Heisenberg showed that by measuring a system, by measuring the position of an electron, you affect the electron. There's no way you can actually measure something without affecting it. This is a big difference compared to the physics before Heisenberg, where it was thought humans could be impartial observers. But we never are, right? If you go off to Africa and decide to live with the apes and in their own habitat, they're going to react to your presence, right? You are not invisible. Your observation of them will affect them. In physics, it's a fundamental property. You can't observe something without interacting with it. A wonderful analogy that I really like is, imagine you're in a large room with a hard floor, like a hardwood floor, and it's completely dark, pitch black, but there's a ping pong ball on the floor somewhere. How would you find it? Well, most of us will get on our hands and knees and start to feel around for the ping pong ball. As soon as you find the ping pong ball, you find it by bumping into it. But by bumping into it, you give it energy, you give it momentum, you send it off in some direction. So you interact with it, right? So by the process of interacting, discovering the ping pong ball, identifying its location, you change its momentum. And the uncertainty in position and momentum, Heisenberg looked at and said, hey, you cannot measure both simultaneously with exact precision. It's impossible. By measuring an electron or by measuring the location of a photon, you interact with it. You change its properties. So the uncertainty principle basically states you cannot both know the exact position and momentum of a particle simultaneously. For example, the position error, because these objects travel as little wave packets, the position error in a particle is about the same as the wavelength of that particle. The momentum error, momentum is Planck's constant over the wavelength. So when you multiply these two things together, delta x times delta p, where delta x is the position error or the uncertainty in the position, delta p is the momentum error or the uncertainty in the momentum. When you multiply these two things together, the lambdas cancel and it's approximately equal to Planck's constant. That's a very rough calculation. A more precise calculation beyond the scope of this class that Heisenberg did shows that the product of the error in momentum, error in position and the error in momentum must be greater than or equal to Planck's constant over 4 pi. You cannot do better than this. The universe prevents it. So if you know what the error in the position of a particle is, you can calculate what the minimum error in its momentum has to be. If you know the momentum in the error in the momentum of a particle, you can calculate using this equation what the minimum error in the position is. And to calculate the minimum error, you basically, rather than treating it like a greater than sign, greater than or equal sign, you treat it like an equal sign and you solve the equation. Again, h being Planck's constant. So this is a fundamental property of the universe. You cannot beat it, no matter how good your equipment is. Alternatively, there's another version of Planck's law. It's called the uncertainty principle for energy and time, which states that the error in the energy of a particle, which if we'll learn we learned we talked about relativity, that energy and matter are basically two sides of the same coin, E equals mc squared. So energy and matter are basically very similar. The error in the energy times the error in the time must be also greater than or equal to h over 4 pi. This has some rather interesting implications. This means that short-lived energy states, for example, at a particle accelerator, when you smash things together, you can create gluons and other tau particles, very short-lived particles. How long those particles live affects the range in energy we can measure those particles. So if particles have a very, very, very small lifetime, there's a wide energy possibility that those particles can cover. Additionally, and we'll learn about this when we talk about the universe later on, it means that the universe can borrow energy as long as it doesn't borrow it for a very long amount of time. So a particle can actually spontaneously be created. A positron and an electron can spontaneously pop into existence as long as they destroy each other within a given time interval. These are called virtual particles, and there's plenty of scientific evidence to support the existence of these virtual particles. So this is Heisenberg's uncertainty principle, two forms, the position momentum form and then the energy time form. It's important to understand that this works at the subatomic and atomic levels, right? These don't apply to the macroscopic world. There's a wonderful joke that shows how silly these are in the macroscopic world. A police officer pulls over Heisenberg, who's driving on the highway. And the police officer walks up and says, "Oh, Professor Heisenberg, I didn't recognize you. I'm sorry. Do you know how fast you were going?" And Heisenberg replies, "No, but I know where I am." And the police officer responds, "You were doing 70 miles an hour." And then Heisenberg throws up his hands and says, "Well, now I'm lost." Right? Heisenberg knew his position, but not his momentum. When the police officer told him his velocity, he calculated his momentum, he no longer knew his position. So again, lame physics joke, but I enjoy it. This is the essence of the Heisenberg uncertainty principle.